Okay, so this week, it's Monday, and this week we're going to talk about chapter 16. The next week we'll do chapter 17, and the following week we'll do chapter 18. Chapter 16's title is Combinatorial and Parallel Synthesis. And these are tools for drug discovery. Now, what a lot of people will do is, in order to find a lead compound, okay, so traditionally, lead compounds have been doing a goal compound based on kind of how you all looked at the drug targets and try to come up with a scaffold, and then you do either a linear or a convergent synthesis. Now, a convergent synthesis is better than a linear synthesis, because if this is your goal compound, a linear will start with A and go to B and then go to C, and you can have up to 18 steps to finally get your goal compound. And then if you want to make a second change on this compound, you have to go through these synthetic steps again. But a convergent synthesis, maybe you can go from A to B to C, and then here you can go from D to E to C, and then C you can go to as many different compounds as possible. And so that is a better synthesis. So convergent synthesis is considered better than linear. Now, combinatorial chemistry and parallel synthesis, this is really in 1980s. It really took off in the 1980s. I was actually one of the first scientists to be in a group. We were actually, when I got hired to Lilly, we were in the combinatorial chemistry group. So we had a little group, it was combinatorial chemistry. So I'm very familiar with these techniques and synthetic tools, because I used them for several years. And then we kind of did away with our combinatorial chemistry group, but we still use the medicinal chemistry tools. So the hardest part is to find a lead compound. Okay, so, and it's really hard. We're talking, gosh, when I was at Lilly, they had 6 years. The infectious disease department did not have one single lead compound. So after, these were great chemists too, so they all got laid off, and some of them got absorbed into different therapeutic areas, and well, that was one of the reasons why we don't do infectious disease. So that's a therapeutic area that we need compounds, but if you can't find a lead compound, then that costs a lot of money, and that will absolve that field. Okay, so like I said, the limiting factor in most drug discovery processes is identifying a lead compound. Now, medicinal chemistry typically will use both traditional optimization techniques, but they also include combinatorial and parallel synthesis to optimize a lead compound. So what I want you to know is, what are the differences between combinatorial synthesis and parallel synthesis. And you will have a quiz again on Wednesday talking about these different techniques on Canvas. And it'll be 10 multiple choice questions. So that's what we're preparing you for. So first we will talk about the parallel synthesis. Okay, so we can just make two columns in our notes. Parallel synthesis and combinatorial synthesis. Parallel synthesis will use standard synthetic routes, that means organic 1 and organic 2 chemistry, to produce a range of analogs. And each vessel, this is a big difference here, each reaction vessel will have be in a separate tube or a well, and it will have a different analog in each of those reaction wells. Combinatorial chemistry uses the standard synthetic routes to produce a probably a larger, okay, so the numbers are a different variety of different analogs. But in each vessel, will contain a mixture of products. Now, a lot of times with parallel synthesis, the identity of each structure is known, and it will produce a range of analogs for SAR, structure activity, and drug optimization. For combinatorial chemistry, the products need to be distinct, physically distinct from each other, and a lot of times they'll be attached to different beads. You identify the structures in each vessel are not known. So the identity in each are not known with certainty. So a lot of times you're interacting here with the target, and then you will go and when you have activity, so if you have something with activity, then you will identify the structure. So you kind of look for the identity afterwards. When you're doing parallel synthesis, you already know exactly what structure is in each well, and you're going after that. So if we keep on with our list here, parallel synthesis is really quality rather than quantity. It's used for focused lead optimization. It's fast and it's efficient. And we'll talk about the different techniques used in each one of these. Okay, so that'll be the next thing we focus on here. Combinatorial chemistry, it's useful to find a lead compound. It allows for rapid synthesis of a range of compounds. Usually you'll have inactive mixtures, and you can store those in compound libraries. So then you can test those molecules in different therapeutic areas. So usually your goal is to make a very large library. Active mixtures, however, active mixtures will then they'll be identified, and they will be further explored to identify the active component. And we'll talk about the different techniques here as well. So we'll talk about different techniques for these two, and that might be like tomorrow's video lesson. So these are the two different ones. I will tell you, like I said, I've done a lot of parallel. So I've done a lot of parallel synthesis. And I do know that now I have a friend, her name's Sarah, and Sarah designs compound libraries. She graduated from Notre Dame. She works at, these are my friends at Eli Lilly, and she's moved out of the lab now, but she designs compound libraries. And then my friend Deanna, I have a friend Deanna, and Deanna is also out of the laboratory now. And she's told me, Beth, you would not believe the large checks I write to our companies in China that get money to synthesize the compound libraries that people, chemists like Sarah, go on a computer and design. When I was at Lilly, we had a company in North Carolina, Durham, North Carolina, and their whole goal was to do compound libraries using combinatorial chemistry methods. Like I said, in the lab, a lot of times I would do parallel synthesis. Okay, so let's look at the different techniques that are used for parallel synthesis. So you want to look in your chapter 16. We're looking at page 362, and I want you to learn a little bit about solid phase organic synthesis. I do know you have some questions on solid phase organic synthesis. And this is really employed heavily in parallel and combinatorial chemistry. And so what are the benefits of solid phase techniques? Solid phase techniques, first of all, there's a resin here, and there's several different resins that you kind of need to be familiar with. And one of them is the Merrifield resin. Okay, so this is Merrifield resin. And then I'll show you the Rink resin. The Rink, yeah, here we go. Here's the Rink resin. And then we'll also look at the Wang resin. Okay, and and we'll look at the dihydropyran resin. Now, solid phase organic synthesis really came about during protein synthesis. So it's how we really are able to do peptides. And that was with the Merrifield resin. And so what the resins do, you can take an amino acid. So you take something like a protected amino acid with your R group here, And you have this protected with a Bach group, okay? So what's the Bach group look like? That's a Bach. And so you Bach protect your amino acids. The Bachs come off in TFA, trifluoroacetic acid. And your resin is this polystyrene bead, and then what happens here is you can make an ester linkage here. So the chlorine is your leaving group, and you make an ester. And so then you can go and you can take off the Bach group and you can continue on the reaction. And then when you want to cleave it, you want to cleave this ester, then you use hydrofluoric acid. And hydrofluoric acid then will release your amino acid. And it will leave you with a carboxylic acid on one end, and then you can have amino acid 1, amino acid 2, and then you get an NH2 on the other end. So that's great for making amide bonds. Now, you look at, and you can do different resins. The Wang resin, you can see the Wang resin is, let's see if we have the Wang. Yeah, the Wang resin is in figure 16.6 in your book, so page 328. And you can see this OH here is also with a carboxylic acid, okay? So it's going to make the ester. And these were all designed really for amino acid synthesis. And here's your R. Now, this R group now is protected by an F-MOC group. And an F-MOC group, you can see that in your box down there, and it looks like this here, okay? And you can see the F-MOC groups come off in using TFA. So once this is still a TFA cleavage, okay, and it'll release your the F-MOC group actually comes off in piperidine. So that's a base. So you can attach this amino acid by the carboxylic acid to this Wang resin. You can deprotect the F-MOC group with TFA, and then the I'm sorry, not TFA, but piperidine. So the F-MOC will come off in piperidine base, and then when you want to cleave it from the resin, then you use TFA. Okay, so TFA cleaves it. Okay, what about the Rink resin? So if you see the Rink resin, that is figure 16.7 on page 329. As you see again, here's the amine group, and the amine now reacts with the carboxylic acid of an amino group. Okay, so you're making an amide bond. And then you can derivatize, do further modifications on the R group. And then when you release it, the functional group is actually an amide. And these are released using acid again. TFA releases that. What I find interesting is the dihydropyran, which is in figure 16.8, and the dihydropyran is a protecting group for a acetal. So let's look at that. I guess that's on figure 16.8. And so this one, you can take basically, you can take a primary alcohol. So if you have a primary alcohol, then that will react with the pyran. This is your functional group, and that is an acetal. and the acetal is cleaved in TFA. Okay. Um, so you do have some examples of solid phase organic synthesis. Basically, you do solid phase organic synthesis, especially for making compound libraries, and you use solid phase chemistry. You can use it for parallel synthesis as well. Okay, our next discussion on chapter 16, we'll talk about the different techniques used in parallel synthesis versus combinatorial chemistry.